Hi everyone, this is Amir here at Civil Engineering with Amir. Today I'm going to solve a problem on truss analysis that is selected from Chapter 6 of Vector Mechanics for Engineers by Beer Johnston. Here in this figure you can see a Gambrel roof truss, and the question wants us to determine the force in each member of the truss and also determine if each member is in tension or in compression. Okay, so if this is a house, the roof of this house will look something like this. So you'll have several trusses similar to this one, and then you'll have panels that goes on top of these trusses. So you can see the Gambrel roof trusses here in the left picture, and in the right one you can see the panels that I talked about earlier. All right, let's start solving the question. This was just to give you an overview of how these Gambrel roof trusses look like. Before I start doing the calculations and solving the question, I want to briefly explain how I'm going to do this process step by step. So first of all, by looking at this truss, you can see that the geometry of this truss is symmetric. So if this is your symmetry line, you can see that the two sides of this line look exactly like each other geometry wise. So the geometry is symmetric. The loadings are also symmetric in the both sides of this line. So we have a 300, exactly 300 on the other side, 600, 600, and we have 600 on the symmetry line. We also have two support reactions, and we know this support reaction is equal to 0 because there's no other force in this direction. So we can say loading is also symmetric. Now, since both the geometry and the loadings are symmetric, we can conclude that this structure is symmetric. So the structure is symmetric. And it's really important that you have to also consider loading. In this question, if one of these forces was, for example, 900 pounds, this structure wouldn't be symmetric because the loading is not symmetric. We have 900 here, but we have 600 here. Even when the geometry is symmetric, when the loading is not symmetric, the structure is not symmetric. So you will have to satisfy both these conditions so you can have a symmetric structure. Now that you know your structure is symmetric, you can say that this support reaction is equal to this support reaction. So if this is AY, this is HY, you can say that AY is equal to HY because of symmetry. And now if we write the equation of equilibrium in the Y direction, so if this is the Y direction, this is the X direction, we have all these forces. If we add them together, this AY will be half of the sum of these forces, and HY will also be the other half. And after we determine these support reactions, we can start solving the question from one of these joints. Okay, say I'm gonna start with this joint. We have the value for AY, we have the value for this external loading, and we have to determine these two forces. And by writing the equations in the X and Y directions, we can determine these two forces. After we determine these two forces, we can move to this joint. Again, we have a force here, we have another force here. We can determine these two forces. And then in this joint, this force is known, this force is known. We can determine these two forces. And then in this joint, since this is a symmetric structure, this force will be equal to this force. And the only unknown force in this joint will be here. And we can determine this force using the equation of equilibrium. And the other forces will be similar to the forces on the other side. Okay, without further ado, let's start the calculations. First of all, sigma Fy is equal to 0 in this direction. So this is Ay, this is Hy, which is equal to Ay. So Ay plus Ay minus 300 multiplied by 2 minus 600 multiplied by 3 is equal to 0. And this will give us an Ay equal to 1200 pounds. And Hy will also be 1200 pounds. So 1200, this is 1200. And now, as I mentioned earlier, I'm going to start with joint A. So at joint A, this is our joint. This is our support reaction. This is our external force. We have FAB and we have FAC. It doesn't matter which direction you choose for FAB and FAC. We don't know the direction for them yet. But in order to simplify the process, I always try to assume that the unknown forces are tensile forces and coming out from the joint. And then if the value that I determined for that unknown force is positive, I know that my assumption was correct and that load was a tensile load. And if it's negative, I know that the member was in compression. So this is joint A. So in the method of joints, in each joint you can write two equations of equilibrium, one in x direction and one in y direction. In the y direction, we can say 1200 minus 300 plus FAB cosine of this alpha is equal to 0. So this will be our FAB cosine of alpha, and this will be our FAB sine of alpha. So this is our alpha. Cosine of alpha will be this length divided by this length. So this is 6 feet, this is 8 feet, and this will be 10 feet. AB will be 6 in the power of 2 plus 8 in the power of 2, the square root of this value, which is 10. So cosine of alpha will be 6 feet divided by 10 feet, or 0.6. 0.6 FAB is negative 900 pounds. And this will give us an FAB equal to 1500 pounds negative. So this means that the direction that I chose for FAB was incorrect, and member AB is actually in compression. So we can say FAB is equal to 1500 pounds, but in compression. Now, again, for joint A, if we write sigma Fx is equal to 0 in this direction, we can say FAC plus FAB this time sine of alpha, and there's no other force in the x direction. These two forces are all in the y direction, is equal to 0. So FAC will be equal to negative FAB sine of alpha. And we know sine of alpha is this length divided by this length, or 8 divided by 10. So this is 0.8, and we know this is 1500 negative. So FAC will be equal to positive 1200 pounds. So FAC is 1200 pounds in tension. It means that the direction that we chose for FAC was correct, and the member is actually in tension. Now, in this diagram, we can substitute these forces. So this was 1500 in compression, this was 1500, and this was in tension, this was also in tension. So 1200, and this is 1200. Now let's continue with joint C. So this is our joint C. We have 1200 here, we have a force here, we have another force here. This is FCE, and this is FCB. So if we say sigma Fy is equal to 0, there's only FCB. So FCB is equal to 0. Now sigma Fx is equal to 0 in this direction. So FCE minus 1200 is equal to 0. So FCE is also equal to 1200 pounds, and it's also in tension. So one thing to remember is that when you have a joint and we have 3 members connected to it, 2 of these members are in the same direction and the other one is in another direction, and there's no external loading applied at the joint, this member is always a zero force member. So here we have member number 1, member number 2. These 2 members are in the same direction, and this third member is in another direction. So if this is an X direction, and this member number 3 is not in X direction, it can be in whatever direction except for X direction, and there's no external loading applied to this joint, this member is always a zero force member, and here you can see that FCB was equal to 0. Okay, so now we have this equal to 0, and this one also equal to 1200. This is also equal to 1200. Now let's continue with joint B. So for joint B, if this is our joint, we have something like this. We know this is 1500. This is FBD. This is 600. And this is FBE. Let's go back and take another look to the geometry. So if we consider this triangle, also this one, and also this one, we can call this alpha 1, we can call this alpha 2, and we can call this angle alpha 3, and we call this point O. So if we consider the triangle BDO, cosine of alpha 1 will be equal to BO divided by BD. So this BO is 8 feet, but we don't know the length of BD. We can say BD is equal to a square root of BO in the power of 2 plus DO in the power of 2, which will be equal to square root of 8 in the power of 2 plus DO is 2 feet and 4 inches. So we know 1 foot is 12 inches. So 4 inches will be 1/3 of a foot. So 2 feet and 4 inches will be 7/3 feet, and then in the power of 2. So this will be equal to 25 divided by 3. So this cosine of alpha will be equal to BO, which is 8 divided by 25/3, or 24/25. And for sine of alpha, it's equal to DO divided by BD, or 7/3 divided by 25/3, or 7/25. So these are for alpha 1. For alpha 2, if we consider BOE, for BE, we can say it's equal to square root of OE in the power of 2 plus BO in the power of 2, or 6 in the power of 2 plus 8 in the power of 2, which will be equal to 10. Now for cosine of alpha 2, we can say it's equal to BO divided by BE, which is 8 feet divided by 10. And for sine of alpha 2, OE divided by BE, and finally for alpha 3, if we consider this triangle ABC, we have cosine of alpha 3 is BC divided by AB, and AB is equal to AC in the power of 2 plus BC in the power of 2, which is equal to 8 in the power of 2 plus 6 in the power of 2, or equal to 10. So cosine of alpha 3 is equal to BC divided by AB, or 6/10, and sine of alpha 3 is AC divided by AB, or 8/10. Now let's move all this here. This is our alpha 1, this is alpha 2, and this is alpha 3. So this will be FBD cosine of alpha 1. This one will be FBE cosine of alpha 2. So they are both in this direction. And for alpha 3, we have this one and we have this one. This one will be 1500 sine of alpha 3. This is also this direction. So sigma fx is equal to 0. We have fbd cosine of alpha 1 plus fbe cosine of alpha 2 plus 1500 sine of alpha 3 is equal to 0. For cosine of alpha 1, we had 24 divided by 25, so this will be 24 divided by 25 fbd plus, for cosine of alpha 2, we had 8 over 10 fbe plus sine of alpha 3 was 8 over 10 again, is equal to 0. So this is one of the equations. And now we can write the equation of equilibrium in the y direction as well. So fbd sine of alpha 1, which will be this force, minus fbe sine of alpha 2, which is this force, minus 600 plus 1500 cosine of alpha 3. So sine of alpha 1, we have 7 over 25. 7 over 25 fbd minus sine of alpha 2, 6 over 10 fbe minus 600 plus cosine of alpha 3 is 6 over 10. 6 over 10, 1500 is equal to 0. And this will be our second equation. So now we have two equations with two unknowns, which are fbd and fbe. And by solving these two equations to unknown, we can determine the values for fbd and fbe. So 1 and 2 gives us fbd equal to negative 1200 pounds, which means that fbd is in compression. So fbd is 1200 pound and in compression, and fbe will be equal to negative 60 pounds. So this is also a compressive load. fbe is, now if we go back to our first diagram here, this fbd was 1200 and it's going into the joints because it's a compressive load. 1200 fbe, it's 60 pounds and it's going into the joint because it was a compressive load as well. This is also 60. Now the only remaining force that we have to determine is fde, because this force is also 1200, this one is also 60, and this is also 1200. So this is also 1200, 1500, 1500. Now, in order to determine this force, we can either use this joint or use this joint. It doesn't matter which one we go. But I personally prefer to go with this one because I feel that it's easier to calculate the angles for this joint. It doesn't matter which one you go with. It's just a personal preference. So I'm going to go with this joint E. So for joint E, if this is our joint, this is our FDE that we want to determine. We have two forces here. These are in tension, 1200, 1200. And these two are compressive loads, 60 pounds. And this is our joint E. Now, if we write the equation of equilibrium in the y direction, we can say FDE minus, we have two forces here, 260 multiplied by cosine of this angle, which we call alpha, is equal to 0. And now if we go back into this triangle, so this is our alpha, this will be also alpha. Cosine of alpha will be this OE divided by BE. So OE divided by BE is 6/10. So this is 6/10. And FDE will be 266/10, or FDE is 72 pounds. And since it's positive, it's in tension. And now we can complete our diagram here. So this is 72, and this is also 72. That's it. We determined the force in each member of this gambrel roof truss and determined if the members are in tension or in compression. Thanks for watching this video. I hope you found it helpful and informative. If you like this video, please press the like button. If you have any comments, suggestions, feedback, or if you have any questions, feel free to write for us in the comment section below. And if you haven't already subscribed to the channel yet, please hit the subscribe button on the right corner and support us. Thanks for joining us today, and see you in the next video.